So I'll say that IARPC is a means for reporting and coordinating Arctic research among the various U.S. government agencies. We are organized into collaborative teams. So today's meeting is a joint meeting between the modeling sub-team and the Glaciers and Sea Level Change team. We welcome researchers, stakeholders, and other interested parties in the Arctic. I was wondering if Joe might have a comment or two for the Glaciers and Sea Level Change team.
Sure, thanks, Richard. So the Glaciers and Sea Level team is interested in what's going on with the Greenland Ice Sheet and Arctic land ice masses, how they're evolving dynamically and what the consequences are to sea level rise, and understanding that for coastal communities around the world. And so we've got an interesting mix of folk from all sorts of federal agencies and university partners as well. And thank you for your involvement. I'm a co-lead, apologies for the noise there. I'm a co-lead with Caitlin Florentine of USGS, who's stepping down and couldn't make it today. But fortunately, I'm going to turn it over to Caitlin Harbeck, who's at NASA HQ, who's joining the team. We have conservation of Caitlin's, and so Caitlin, would you like to introduce yourself and join the team?
Yeah, sure thing. Thanks, Joe, and thank you, Vivian. Nice to meet you as well. Yeah, hi everyone. My name is Caitlin Harbeck. I started working at NASA headquarters in the Cryospheric Sciences program there in January, but my history with NASA goes a little bit further back than that. I was part of the ISAT-2 Project Science Office at Goddard before that, so I've known Joe for a little bit, and but I'm excited to be a part of IARPC and to help coordinate these meetings along with Meredith and the rest of the Glaciers and Sea Level collaboration team.
Thank you, Caitlin, and welcome aboard. Okay, so without further ado, we'll get to today's meeting. So Greenland has been in the news over the last week with the rainfall event at Summit. I think today's topic is more along the lines of the business end of the ice sheet. So iceberg calving, or the ablation of glaciers at the marine termination, is a difficult process to model because it's inherently very complex. And there are tremendous difficulties associated with obtaining quantitative observations. So today we're going to get a perspective on current progress towards the modeling of iceberg calving. We're going to hear first from Tim Bartholomew. He's a professor at the University of Idaho, and he will speak on improved predictions of iceberg calving at Greenland's outlet glaciers. Tim, take it away.
Great. Thanks, Richard. So I appreciate that description of working at the business end of the ice sheet, because I think it's kind of how I do think about it. I've got a couple of photographs here from Alaska, Greenland, and Antarctica, actually. I'm also privileged. I want to give a shout out here to my co-authors, Tristan Emerald and Chris Miele, who are two graduate students that I've been with here at the University of Idaho. And then also my collaborator on this funded work at Boise State, Ellen Enderlin. And I'm not today in the Arctic. I'm now actually on the home of the Nez Perce, or the Nimiipuu people here on the Palouse in northern Idaho. Here's the University of Idaho in Moscow, kind of underneath Moscow Mountain. And just last week, my research group gathering to kind of start to coalesce here at the beginning of the semester. I've got here Bruno, Vernice, Chris, and Yoram all with me. Dakota's wasn't with us on this day, but these are some of the folks whose great work I'm getting to present today. So as you've seen, outside of Idaho, or outside of where you may all be, that our ability to project and better understand and simulate tidewater glaciers and tidewater glacier change is really rapidly improving. And so we've seen that in terms of Andy Ashwanden's work showing the importance of increased resolution in ice sheet modeling. We've seen the results of simulation of individual glaciers and their response to frontal ablation or changes in submarine melt. We've got the increased simulation of outlet glaciers here at an entire ice sheet scale and at a continental scale. But one of the things that's really difficult about these kinds of simulations, and what's bringing us here today, is this work on iceberg calving. And this is a slide some of you may have seen before, but I've got here 4 different examples of iceberg calving, and I think that these visualizations really nicely show why calving is such an important and really challenging problem. Right here, we've got second by second variations of Serac failure in Idaho. We've got minutes by minutes of slab capsize in Greenland. We've got weeks of ice shelf splintering in Antarctica, and then months of tabular rifting in Antarctica. And all of this is what we call calving, right? We seek one kind of understanding of calving without typically really acknowledging that we've actually got a tremendous variety of different forms that calving can actually take. So no wonder it's such a stubborn problem. And it's an important problem because about half of Greenland's mass loss occurs through processes such as these. And so this is until we can simulate these kinds of processes accurately, we're not going to have a good handle on projections of future sea level rise. And so we work with that in terms of in the ice sheet model environment through what I'll call calving models, or sometimes called calving laws. And each of these is a parameterization based on some physical understanding of how things ought to work at the Tidewater Glacier terminus. And either these predict the location of the terminus or the rate of ice loss from that terminus. So we've got either a position model or a rate model. And typically speaking, that these tools are used to understand or proposed or validated at a couple of locations or at a couple of the target systems. And in reality, while we acknowledge that some remelt is a tremendously important process and in some cases can be a major driver of iceberg calving, for the purposes of this talk, for the purposes of this research, I'm just going to sort of rope it in with calving and acknowledge that as a sort of potential shortcoming and an opportunity for improvement in this work. But as we try and better understand the proliferation and the improvement in those calving model parameterizations, those calving models, we've got 2 potential ways of trying to understand how well those calving models do at actually simulating our observed ice sheets. And so the first of these 2 approaches is to tune an entire ice sheet model and to say, we have achieved our goals when the entire model reproduces our observations of ice sheet mass change or calving mass loss or glacier flow. And in this case, we apply one of those calving models to what other model output, to the modeled ice thickness or the modeled velocity. And this is tricky because ice sheet models, in reality, as probably most of you know, have at least 4 major and separate and independent concerns, none of which are settled science. And the first of those is the rheology of the ice, the continuum mechanics, but then we've got the boundary conditions. We've got the surface mass balance, the top boundary condition, we've got the sliding law or the bottom boundary condition. And then at the front of these glaciers and ice sheets, what I'm going to be focusing on today is that calving or melt model, that frontal boundary condition. So we've got 3 boundary conditions and the continuum mechanics, all of which have to be right. And the trick here is that when we are applying these calving models to the modeled ice thickness or velocities, we could actually do a pretty decent job of simulating observed ice sheet behavior, but by sort of having canceling errors. We could get the right fit for the wrong reason. And so my suggestion here is that we can take a different approach to understand what is the appropriate frontal boundary condition, what is the appropriate calving model, by isolating that calving model and just calibrating its performance, evaluating it independently of the rest of the ice sheet model. And in that sense, we apply that calving model to the observed ice thickness and the observed velocities. And this is the approach, this isolation of the calving model, and compare and leaning on our observational data sets as much as we possibly can. This is what was published recently last year by Tristan Amaral, myself, and my collaborator, Ellen Enderlin, in JGR. So look for this paper. I'm just going to touch on some of the kind of high-level results of this in the next few slides. So to do this, we're incorporating a lot of this sort of now common, but 10 years ago, glaciologists would have, I don't know, run out to the street or mug somebody to get their hands on these kinds of data sets, right? We've got bed elevation data sets, ice elevations, velocities, all of which are now with great spatial resolution and with great temporal resolution. We take these observational inputs, apply our calving models to that, and then do this testing at 50 different glaciers all around Greenland that represent a whole range of different flotation states, fast glaciers and slow glaciers, northern latitudes and southern latitudes, a variety of thicknesses, and we look at a variety of different temperature times of year. And so we're looking at sort of spring and early summer, and we bring together all of this data set to try and understand calving at all of these different potential sample glaciers. We then try to minimize the misfit between the observed calving and the observed between the observed calving and the modeled calving, where we might say one misfit might be the difference between a predicted and an observed terminus position, right? Because we've got one of these classes as position models. The other misfit is going to be a calving rate misfit, not a position misfit, but a rate misfit, where we've got some measurement of how quickly we can observe frontal ablation taking place, how quickly we can observe calving taking place, and then compare that with our modeled calving rates. And but to say that we're going to do this not just at one glacier, but we're going to do this at each of 50 different glaciers and with each of 6 different calving models and a whole range of different parameter values for each one of those calving models, because each of these calving models has at least one poorly constrained parameter that goes into that model, whether that be a height above flotation or some stress, tensile strength threshold. And in practice, at a single glacier, you might say that the glacier is advancing at about 9 meters per day, and also at the same time calving back at 5 meters per day. Here we're looking at a cross-section, a topographic cross-section of the glacier above sea level. And we can anticipate that, well, for example, for one of these calving models, the von Mises criterion, which is one of the more popular calving models now, that calving rate depends on one of these parameters, sigma max. Sigma max represents something about the strength of that ice. And so we can vary that parameter, say initially assume that it's 0.2 megapascals, and we get a calving rate error that is 10 meters per day. We overpredict the rate of calving. If we choose 0.65 megapascals, then our modeled calving rate is 5 meters per day and we have 0 error. And if we chose a larger sigma max, then we get a negative error that we underpredict the rate of calving. And so in this case, we would say that for this glacier, for this one instance, 0.65 megapascals, that's the right parameter to use for this calving model. But we're going to do this actually at all of the different glaciers and try and identify what is that misfit if we choose one single value for the entirety of the ice sheet, which, it is all ice, with maybe different ice temperatures, but we expect that the ice sheet ought to behave, we ought to have good performance of a model in the north, just as we do in the south, and on the west, just as we do in the east, and look at those different misfits. And here we can see how well do these different calving models perform in different locations. We can also do that look at the bias or look at that error with these different rate models, the von Mises criteria or the stress maxima model. And to kind of cut to the quick of this one, through consistent application of these calving models and use of their parameters and single parameters across all glaciers and across different seasons and different years, we've been able to identify the single best calving model for use with all of Greenland's tidewater glaciers now and in the future. And that model that we recommend is one of these calving position models. It's the crevasse depth model. We found that the parameter here in this case is a water depth that performs extremely well. And by extremely well, I mean, we want to have low uncertainty, right? So low aggregate misfit across the entirety of the ice sheet. And then also we have some humility in that this parameter value of 25 meters might not be exactly right. And in the likely case that it's not quite right, we want to have low uncertainties for small variations in that parameter change, right? We want low sensitivity to potential inaccuracies in our model. And so with that, we can recommend the crevasse depth model. For more details on that, I want to recommend and refer you to that published paper, Amaral et al. 2020 in JGR. One of the interesting observations that we followed up with, that paper that Ellen led and published in the Cryosphere also last year, is that this crevasse depth model and the water depth actually has no physical basis as a water depth. And so that's a source for other future work, right? That this potentially that we are underestimating or overestimating the strength of the ice, that this sort of assumed water driving down the depth of these crevasses, it has the right numerical impact, but it's the wrong physical way to be thinking about this water depth. I want to pivot slightly back to that set of these calving visualizations. And just as we burrowed into the process of calving across a range of views, I want to burrow into this specific mode of calving, right? This particular tabular rifting mode of iceberg calving. And here we see one of these major tabular bergs rifting off from Pine Island Glacier. And one of the interesting observations is that we see along the margins of these rifts, these really consistent, actually darn near periodic feathered fractures along the edges of that. And so this was an observation, and the commonality of this, I think we've probably seen this at some of the Erebus ice tongue. You might recall that in some of that classic imagery, but it's really quite ubiquitous everywhere we have ice that is sort of starting to detach from its sidewalls. And so here we have an image of Petermann Glacier from July 2012. We see some of that feathering. It's been traced in this Landsat image just so it pops a little bit better. We've got one of these rifts coming in from the side here. Ice is flowing in from the bottom of this screen. Here's a one square kilometer square for scale. And as we lose sidewall contact from these fjords, right, as the ice seems to separate from its fjord walls, then we get this onset of feathering, these sort of detachment rifts. And sure enough, a few weeks later after this initial imagery, we have calving. We have an iceberg tears off that had originated at one of these rifts. And so we see that ice shelves, they decouple from the sidewalls, and rifts form from the margins inward. They penetrate inwards from the sides. And so this at Greenland's ice shelves and floating ice tongues, and actually at most ice shelves in Antarctica, this is the major driver. This is how ice shelf calving actually progresses. This isn't exceptional at Petermann. We also see it at Ryder. Here again, we see detachment, feathered rifts at the edges where we start to get a float. We have a nascent iceberg here. And days later after this image, that iceberg has completely detached. The rifts have gone through, and originating at the place where we're starting to have detachment from those sidewalls. And even at 79 North, right here we have already, this is a floating ice shelf, but that ice shelf is being pushed around a couple of major pinning points, little bedrock islands that are identified and traced in black here. And we see that, that where we have shear and where we have detachment, we have increases in these feathered rifts. I see that I'm running out of time here. So I'll pick up the pace a little bit. And again, this produces icebergs. So one of my students, Chris Miele, was able to simulate this in the ice sheet model ice pack that's run by Dan Shapiro at UW. And where we've got full coupling at the sidewalls. Here we're looking at a color map of the velocity of this glacier. This full coupling on the sidewalls, here's the glacier terminus. Here we lose contact with the sidewalls and we have free slip down glacier of this position. And we transition from sort of plug flow with lots of lateral shear and confined ice shelf flow up glacier to unconfined ice shelf flow down down towards the terminus. And this transition in coupling leads to a major shift in the flow regime. And that flow regime from a confined shelf to that unconfined, that decoupled flow leads to a lot of acceleration. And as you can anticipate, a lot of stress, a lot of tensile stress along these margins. That produces rifts in these transition zones. So this shift is sufficient, and we're continuing to pursue this. This shift is entirely sufficient to explain these observations. We're able to model what are those stresses, what are those tensile stresses. And so this identifies and reproduces a really critical rifting mechanism that's common throughout the ice sheets. So the summary for this element here is that observations and models of these detachment zones are really showing a kind of a new or at least underappreciated stresses and are likely to reveal the processes that drive the complete disintegration and collapse of floating tongues and shelves, and would potentially, if the marine ice cliff instability were a thing, this is what we're talking about. We're talking about the collapse of these kinds of floating ice shelves. And for more details here, follow some of Chris's forthcoming work. So just to wrap up, through observational and theoretical studies to isolate key processes, we've been able to advance our understanding of the processes of calving and provide sort of sea level rise projection ready model improvements by thinking about new ways to think about stresses, what are the appropriate boundary conditions to improve model fit, and finally, working with some of these rapidly developing early career colleagues has been a super amount of fun for me. So thanks very much for your attention, and I guess I'll stop there.
Thanks very much, Tim. I think we'll take a couple of questions here before we go to the next speaker. There are a lot of questions. Let's start with, I think Bob Hawley raised his hand first.
That was just me clapping.
Oh, clapping, sorry. I misread the Zoom. I see.
I appreciate that too.
Okay. I see Jack Dibb has his hand raised.
Yeah, Tim, that was great. I was just wondering if that the last topic you're talking about, the rifts growing in from the edges on these ice shelves, applies to some of the really massive tabular rifting or calving events that are happening down in Antarctica, where you get, these gigantic icebergs. I'm thinking like of the one that's threatening Holly 6 or some of the other, many miles long icebergs that have broken off in the last 4 or 5 years.
100%, Jack. And thanks for that question. I mean, when you look at the progression of A68 that was in the news maybe 4 years ago from Larsen C, it originates from one of these pinning points from what we would call a detachment zone. And that rift sort of tears open from that detachment zone. And so it's that transition in flow regime and stress regime that drives this kind of iceberg calving. And so this is particularly relevant because there's this idea, that's been sort of circulated the name of the lead author is escaping my mind at the moment, but this idea of a sort of a safety band around of sort of passive ice shelves that are protecting the interior ice sheet. And that is a safety band if calving progresses from the terminus inland. But if you can just go in from the side, you rift all of this ice, and it's not actually how much ice is downstream of these detachment zones is actually irrelevant to the future trajectory of these ice shelves.
Joe, do you want to ask your question?
Sure. Thanks. And thanks, Tim. That was very interesting. I'd like to probe what you mentioned of I can understand the operational value of the 25-meter water depth for crevasses and using that in a particular calving law. But you also mentioned that would be valuable into the future as well. And I'm thinking of an analogy here with a common criticism of basal friction inversions using single static velocity fields. And then, well, what if the velocity fields involves in the future? Does that inherently mean the basal friction is changed over large areas? So how do you know with confidence that that 25-meter water depth is going to be valuable into the future?
Yeah, that's great. Thanks for that question. I think that one of the keys here was by looking at different times. And so by saying, okay, well, what is the performance of these different models during different seasons when we have potentially different amounts of frontal ablation? And so here we've got one of those figures, and we've got observations from March all the way through November at different seasons when we have different amounts of melt. And we're able to say, okay, well, how is there variation in that optimal parameter that depends on these different seasons? How does our model performance depend on how much melt there is? Is it cold or is it warm? Are we in the ablation season or not? And so, and then, how does this performance depend on whether or not the glacier terminus is a little bit further downstream or a little bit further upstream, right? If we have a different glacier, i.e. the glacier is in a different position, do we get a different performance or a different misfit? And so we've been able to kind of vary some of those knobs to say, yeah, the ice sheet is changing. How sensitive are our results going to be to a changed, evolving ice sheet?
And Matthew Hoffman, could you unmute and ask your question?
Yeah, thanks, Tim. I just had a general question if you had any insights on the usefulness of rate versus position laws based on the tests you did.
Yeah, so this is a phenomenally good question. And I think that one I can't say that we've totally resolved this, but I think it seems as though if you're wrong a little bit at a time in terms of your position, then the ice sheet still is about the same size. In fact, some of these position models are on average wrong by maybe 100 or 200 meters, which at this point is like a grid cell in a model. Whereas some of these rate models could be wrong by 10 meters per day. And so if you're wrong on calving by 5 or 10 meters per day, every single day for a century, you are really wrong in terms of how much ice is being lost from these ice shelves. And so we think because of those compounding errors, we think it's probably smarter, probably better to get the terminus position right, or be a little bit wrong in the terminus position versus be a little bit wrong in the calving rate, and have mega errors in terms of what your mass balance is.
Okay, thanks.
And finally, we have a question from Juliana Marson.
Yes. Hi, team. Thank you for the great talk. I'm an oceanographer, so I know nothing about calving models. But what I'm really interested in is when icebergs, are formed and then drift into the ocean. So I was wondering if those calving models, they output the characteristics of the iceberg formed, so their sizes or their volumes or something like that.
These models do not, but I think, but the style of calving absolutely depends on, what, or the style of calving is directly leads to the size and distribution of these kinds of different icebergs. And I see that my collaborator Ellen Enderlin is on the call, and I know that she is actually working on specifically trying to understand some of those fragmentation processes.
Right.
What is the distribution of the icebergs that is produced by this variety of different glaciers? And I know that she's leading up a talk on this at AGU this year. So either I'd say converse with her in the chat or look for her talk at AGU.
Yep. Hi, Ellen. we have been talking about that. So yeah, thank you for your answer then.
Great.
Okay, I think, thanks very much again, Tim, for the presentation. I think we're going to move on to the next speaker, who is Trevor Hillebrand, a postdoctoral research associate at Los Alamos National Laboratory. And he will speak on sensitivity of sea level rise projections from Humboldt Glacier, North Greenland, to iceberg calving physics. Welcome, Trevor.
Let me share my screen here.
That's
okay.
Good.
Great. So yeah, happy to be here. Thanks for inviting me. I'm going to talk today about a modeling study we've been working on at Humboldt Glacier, looking at sea level rise projections over the course of the 21st century. And today I'll specifically be focusing on how our assumptions about iceberg calving play into the uncertainties here. So this is a satellite image of Humboldt Glacier. The glacier is flowing from the bottom right towards the upper left. Everything out here to the left is sea ice. And this glacier is remarkable because this calving front is about 100 kilometers across. So it's by far the widest outlet glacier in Greenland. So Humboldt is projected to thin and retreat significantly over the course of the 21st century. This figure on the left is from the recent ISMIP-6 multi-model ensemble of Greenland Ice Sheet projections. And I've outlined Humboldt Glacier in purple here. And Humboldt is equivalent to about 19 centimeters of global mean sea level rise. So its future behavior is definitely something that we want to be able to constrain. Over the observational era, Humboldt has lost the greatest amount of grounded, or greatest area of grounded ice in Greenland, about 280 square kilometers since the 1990s. So this is that same satellite image from the first slide, and I've overlain terminus positions from 2000 to 2017 here in these colored curves. The northern terminus has been retreating over that era, while the southern terminus has stayed relatively stable. So we've seen about 10 kilometers of retreat along this fast flowing portion of the northern terminus. Now, if we strip away the ice and look at the bed topography, this whole area here in gray is grounded below sea level with this deep trench below the fast flowing part of the northern terminus here. And if we look at velocity time series along this cyan curve, which is approximately a flow line, we see that between about 2007 and 2017, ice flow tripled in speed at the terminus, and tens of kilometers up glacier, we have seen a roughly 50% increase. So this is raising concerns that Humboldt could be entering a phase of rapid retreat. So with this project, we're trying to estimate how much Humboldt would contribute to global mean sea level this century, and how strongly this depends on our assumptions and about iceberg calving. So to do this, we're using a 3D higher order ice sheet model called MOLLY, which is the ice sheet component of the E3SM Earth System model. And we use this 1 to 10 kilometer unstructured variable resolution mesh, which I'm showing here on the right that's just covering the regional domain for Humboldt Glacier. So we use 1 kilometer near the glacier terminus where ice flow is relatively fast and things are likely to change, and 10 kilometers towards the ice sheet interior where there's slow flow speeds and little change anticipated. And we use 3 different climate forcings provided by ISBIP 6, 2 from CMIP 5 and 1 from CMIP 6 for these ICP 8.5 and SSP 585 scenarios. So to get our initial condition, we first need to compile velocity and thickness observations at the year 2007, which is a quite complete year for observations at Humboldt Glacier. And then we invert for basal friction. Specifically, we're solving to optimize this parameter mu, assuming that the basal traction is this power law relationship, which is dependent also on the pressure at the bed times ice speed to this power less than 1. So then plugging this into the forward model, we get good agreement with the observations shown in panel 1. Thank you. But this is, of course, for an assumed value of Q. And so we can do this, we can recalculate this parameter mu for any value of Q we want. So recalculating it for any given value of Q, we then run this forward with forced retreat at observed rates to 2017 and compare this against the observed velocities of 2017 to tune this friction parameter. So we do this for a range of this exponent between 1/10 and 1. And here's the RMS velocity misfit for 3 velocity bands. And we choose this sort of middle range in which we're getting a good agreement to observe velocities across all 3 bands. So 1/5 to 1/7 we find is our optimal range here. So for these this ensemble, we're using 2 different Iceberg Calving laws. So the first is just a fixed terminus position at 2017, where we just assume that after these basal friction tuning runs, that calving is only sufficient to keep the glacier at that observed 2017 margin. And this is handy because it requires no further tuning or assumed relationships about the dependence on strain rate or stress. But of course, the con is that it's only going to provide us a minimum mass loss estimate. And so next we use this more sophisticated von Mises stress calving criterion that Tim has already talked about, which sets the calving rate C equal to the ice velocity times the von Mises stress at the terminus divided by some threshold stress sigma max, which we treat as a tuning parameter. And this is great because it allows for evolution of the glacier based on the stress field, and it has tended to produce reasonable calving front geometries in Greenland. But it's been found that it requires this assumption of an upper bound on calving rates, and I'll get into this next. So in the previous literature, modelers have used an upper bound of 3 kilometers per year on this von Mises stress calving law, and that's the rate of iceberg calving, not the rate of retreat. And so what we did is tested the sensitivity to this assumed upper bound using 1 to 7 kilometers per year and a case with no limit. And so these time series on the left show the glacier volume above flotation for each of these cases, and you see we get a tripling or so of mass loss over the century between our most conservative and this no limit assumption. And so I just want to show you what this looks like for a 3 kilometer per year calving limit, where we get a steady grounding line and terminus retreat through the course of the century. This pink contour being the grounding line, this white contour is where the bed is at sea level. And then if we use no limit on this calving rate, we see these huge pulses of thinning and retreat that are unphysically fast, and basically the entire marine-based portion of the glacier is deglaciated by 2070 or so. So we can make an estimate of what a reasonable upper bound on this calving law should be based on the modeled glacier speed, which is shown in this bottom left plot. So for the case with no speed limit, we see anywhere up to 40 kilometers per year, and these huge spikes exceeding that. And these are unphysically fast glacier flow speeds for Greenland, so we can discard that, and we get these same huge surge events in the 7 kilometer per year case. So we think anywhere from 1 to 5 kilometers per year is a reasonable upper bound on this calving limit, and it gives us about a 15% uncertainty in our mass loss projections. So these are just the spinal states at 2100, again showing this huge mass loss compared to the 3 kilometer calving limit. Okay, so we need to tune our von Mises stress threshold for this set of forward runs, and we find that anywhere from about 150 to 200 kilopascals gives us reasonable rates of retreat at Humboldt, and above 200 doesn't really allow the glacier to retreat. So for every pair of climate forcing and basal friction law, we run the model from 2007 to 2018, and we score this against both the observed velocities and the terminus position for 2017 to 2018. And then we choose the 3 best values of this sigma max parameter. And so in this case, we see that we're getting a worse fit with increasing sigma max over 1 or 2 velocity bands, and a better fit over 1 velocity band. And we also get this trend in the distance to the observed margin. And so we take this sort of center range of values. And so these are the results for our entire ensemble, including 3 climate forcings, which are represented by each panel, 2 basal friction law exponents represented by the line style, and 4 treatments of calving represented by line color. I've also included a handful of runs with a linear basal friction law just to show the effect of tuning this basal friction relationship on mass loss. So we find that the minimum mass loss scenario in these gray curves here gives us about 5 to 6 millimeters of sea level rise by 2100. That's using a fixed calving front at 2017. And really all the variability there is between climate scenarios. There's very little effect of that, of these 2 different basal friction laws. But if we use the von Mises stress calving law, which is in cyan and blue and purple, we start to get different estimates for different basal friction laws, and so between all of these climate scenarios, we get about 6.5 to 9 millimeters of sea level rise from Humboldt Glacier. Now, an interesting feature of these simulations is that we get a sizable ice shelf by the middle of the century, and this is not something that's generally expected for Greenland glaciers. And in fact, some studies just don't allow floating ice to form at all. So here's our initial condition with just a few floating cells at 2007, and at 2055 we have this sizable ice shelf. So these are time series for all the model runs showing the change in floating ice since time 0, and in some scenarios that shelf just melts away or calves away, but in many of them it sticks around through the whole century. So we want to know if this shelf is dynamically significant. And to determine this, skip the slide. To determine this, we just simply took a subset of our ensemble, removed the ice shelf in that run at 2055, and did not allow it to regrow. So I like to think of this as sort of a crude estimation of what would happen if ice shelf hydrofracture were to initiate. Of course, this is a very, very crude estimation. So it really just shows us the sensitivity of the model to that ice shelf. And for each of these lower curves, this is the corresponding run without an ice shelf, and we get about 1 to 2 millimeters more sea level rise by 2100, which is up to about a 25% increase. So this is a dynamically significant ice shelf. Okay, so in summary, we've tuned this higher order ice sheet model to observations at Humboldt Glacier to determine the likely range of sea level rise over the 21st century. And this range is really dependent on your assumptions about iceberg calving. So with our minimum mass loss scenario, with a fixed calving margin, we get 5 or 6 millimeters by 2100. And really that variability is all dominated by the climate force. But if we use this von Mises stress-based calving parameterization, we can get anywhere from 6.5 to 9 millimeters of sea level rise. And here the variability is due to climate, due to the calving tuning and our basal friction law. And we find that this upper bound on calving rates is a very key source of uncertainty. And finally, we find that an ice shelf grows in the majority of our model runs and it significantly reduces mass loss. So the outlook, we're working to apply this workflow to the whole Greenland ice sheet in the future. And we specifically want to explore the seeming interaction between calving and basal friction. And this could in the long term include coupling subglacial hydrology to ice dynamics. And I think, as we all have probably seen from Tim's talk and other work, improvements to calving parameterizations are really key to reducing uncertainties in century scale sea level projections. And so the ultimate goal for work like mine is to couple these calving fluxes to Earth system models like E3SM, where the ice sheet provides freshwater fluxes to the oceans and the ocean temperatures then feed back into calving. So thank you.
Thanks very much, Trevor. I'm going to quickly ask a question that Juliana Marson asked in the chat. So you use the ISMIP oceanic boundary conditions as well, which specified ocean temperature profile. Is that right?
So we use it specifies an ocean temperature at the seafloor. So for ISMIP 6, the melting parameterization is for a vertical calving face, and so we have this parameterization that controls melting at a grounded terminus, which we find isn't terribly influential over the course of the century. But because we have this ice shelf, we then needed to have 3D ocean temperatures, and so we used depth profiles from CTD data around this fjord to get the vertical structure, and then modulated that based on the ISMIP 6 temperatures.
I see. You had profiles of the ocean temperature, probably from oceans melting Greenland or something else like that, right?
Yeah.
Okay. Okay. Are there any other questions? I see Joe McGregor has his hand up first.
Sure. Thanks, Richard. Thanks, Trevor. Great talk. Couple questions. One is you mentioned for the stress parameter you selected for the von Mises law, some of the projections you felt had unrealistically high maximum velocities. Now, 40 kilometers per year, I agree, is pretty high, but 10 kilometers per year at a near terminus speed is not unprecedented in Greenland. So I was just wondering how you thought about that. And then second, what was the major challenge in this study for what you guys did? Was it setting everything up in the model you selected? I'm getting the impression it's not the calving laws that you used, which is maybe good in terms of evaluating the different calving laws in different places in the future, but maybe more the model setup. Is that impression correct?
So the first question was about the upper bound on calving limits. So yes, you're correct that 10 kilometers per year is not at all unprecedented in Greenland. Let me share this again. So we have this 1, 3, 5, and 7 maximum calving rates, and there's no limit. So this is a log scale on the y-axis. We get up to 40 kilometers. This is 30 kilometers per year on for this no limit, but this 10 or 7 kilometers per year limit also gives these these short-lived but very large spikes in velocity, which we've chosen to discount. So we think this 5 kilometer per year limit is a reasonable upper bound, and that gives us 10 kilometers a year of maximum surface speed. Yeah. So the reassuring thing is that within this sort of reasonable range of maximum glacier speeds, we also get, we get a large uncertainty, but we don't get a 300% uncertainty in mass loss over a century. We get something more like 15 to 20%. And so we think, given all the uncertainties inherent in this, that's a reasonable uncertainty to live with. Your other question about what the most difficult, well, one great difficulty is that BedMap version 4 came out right after I finished doing all my model runs, so I went back and had to redo everything. Another great difficulty is so for the calving parameterization that we chose, it leads to pretty realistic calving front geometries within this range of speed limits. But of course, we have to tune that for every single case. So constructing the ensemble and tuning it is maybe not difficult, but it's certainly a task. And then, when you do all your model runs and find out that there's an ice shelf that you then suddenly need to account for basal melting. Is that good at what you're asking?
Yeah, definitely. Thank you. Yeah.
Okay, there's a question in the chat from Igor, which asked about the surface, whether there's surface glacier melting, and I believe that's covered by the ISMIP experiment prescription. Is that right, Trevor?
Yes. So we have a surface mass balance forcing from ISMIP 6, which is the MAR 3.9 regional climate model, and then that also, the runoff from that model is also routed to the glacier front, provided by ISMIP 6 as runoff of the glacier front. So that feeds into our terminus melting parameterization. Yeah.
Okay, if there are no other questions, I think I can feel free to ask my dumb atmospheric science question here to Tim and Trevor. I had a colleague who used to work on melange in the ocean, and so isn't the ocean state a primary, or not a primary, but a significant mechanism here? How isolated the fjord is, whether the tides are large to induce a stress. Are those incorporated? How would those be incorporated into the model? Tim, I think I'll start with you.
Sure. I think, well, I may here state an unpopular opinion, but I'm not 100% sure that melange actually is long-term important. I think that it invariably affects the timing of calving, but the annualized rates of mass loss from calving, I don't think that's been established yet. It could be though. How is that accounted for? With respect to the observational data sets that we are taking into account depend on, for example, things like the glacier, that these calving models depend on is things like the height above flotation, so the ice thickness at the terminus, and the velocity at the terminus, or the strain rates at the terminus. And so if melange is impacting the ice thickness and the velocities at the terminus, as it ought to be if things are in stress balance, then the presence or absence of melange is actually incorporated in the estimation of rates and positions from some of these calving models, because it affects the geometry and strain rates.
Right. Okay. I remember a story where there was one of these, massive earthquakes in the Pacific, and the resulting tsunami was said to have released, many icebergs as it reached Antarctica. So is the isolation of the embayment and the tides, would they figure as significant factors in this? Or is that just the timing, within a few days or so or months of when an iceberg is actually released, and it's not important?
That I don't know if I can speak to, because I think that if things are linear, then maybe they cancel out. If processes are non-linear, then you maybe have periodic fluctuations that have non-canceling impacts. That sort of the amplitude of the tides you might get, say, more calving on the high tide than you have diminished calving on the low tide. And so potentially that is important. Hopefully by, say, in the study that I presented, by looking at a large enough suite of glaciers, you maybe don't have to worry about some of those details.
Okay. It is 4 o'clock, and Tim, I know you said you had to go. Trevor, do you have a perspective on the questions I asked?
So, yes. So especially for Greenland fjords, no ocean model really resolves a fjord. Even for Humboldt Glacier, which is probably the widest fjord in Greenland, it's the closest ocean temperatures from the closest ocean states from these models are many kilometers away. So ISMIP 6 has done a great job of extrapolating and interpolating those temperatures for us to use. We're fortunate enough to have the observations from oceans melting Greenland, but that will give us part of it, but of course won't tell us whether the fjord geometry is going to affect how ocean temperatures evolve in the future. So that is a big challenge looking forward. As far as melange goes, so Tim's right that you'll incorporate that into your initial condition with these inversions, but what might not be incorporated is what happens when the melange goes away, and you suddenly don't have that back pressure. We've done some experiments. It was over a year ago now that we tried suddenly removing a melange layer at the glacier front and seeing if that could explain the speed up. And I think that's sort of it's an interesting and promising avenue, but I also think that Tim's right that in the long run, melange isn't going to really save a Greenland glacier.
Okay, I should have said it's 4 o'clock Eastern time, but it's the top of the hour. I think this was great. I thanks very much again to Tim and Trevor. Thanks for everyone's questions and participation. And Joe, do you have any last words? What's your next meeting on?
That is TBD. It'll probably be mission updates for ISAT 2 and Grace follow-on, and Caitlin's going to help us organize that. And yeah, that's our current state. But because I've been on, we've slowed down a little bit.
Yeah, well, sorry, Joe. Since this meeting is happening so late in the month, that meeting is tentatively scheduled right now for October 14th.
Okay.
And it'll be a joint meeting with the Glaciers sea level collaboration team and the sea ice collaboration team.
Okay. And I think the modeling team will meet at this time next month, and I believe the topic is program managers from modeling agencies discussing modeling efforts. And with that, I think we're done. Thanks everyone again, and we'll see you next time.
Thank you.
Thank you.
Thanks, everyone.